All right, so let's look at week 4. This is going to be about statistical presentation of data. And this is done with numerical descriptive statistics. So descriptive statistics, again, this branch of statistic refers to the summary of important aspects of a data set. Here one collects data, organizes the data, and then presents the data in the form of charts and tables once numerical measures have been calculated from the raw data. We have measures of central location or central tendency. These are the mean. This is a primary measure, also known as the average. Basically, you add up all the values of the data set and divide by the number of data values. Now note, it's highly influenced by outliers. The median, the middle value of a data set when arranged from smallest to largest. This is useful when outliers are present. Then we have the mode, the most frequently occurring data item. There may be no mode if there is nothing that occurs the same, or there may be more than one mode as well. Now we also have the weighted mean and the trim mean. The weighted mean, we take the sum of the x times w divided by the sum of w, where x is a data value and w is the weight associated to that data value. And we also have the trim mean. And if we do the trim mean 5%, what we do is we order the data from smallest to largest, delete the bottom 5% and the top 5%. Now 5% is not a whole number, round to the nearest integer. And then we'll compute the mean of the remaining 90% of the data. So let's look at some calculations here. All right, so here we have a set of data. What we have is, this is the port name for crossing a border. We have the number of vehicles in thousands that cross the border each year. So what we're going to do is we're going to look at this data and we're going to find the mean, the median, and the mode. Okay. Well, the mean we can do is just going to use the function in Excel equals average, and then we highlight the data. Okay. And then for median, it's going to use the equals median and then highlight the data. And then the mode, we're going to use the multi-mode. So we're going to use mode.multi. And so for instance, if you hadn't known this, but you knew you're going to look for the average, you could start typing average, and then we have our average. And we're going to then have to select the data. So we highlight the data we want to use and hit enter. Same thing with median, we could do that, and same thing with mode. Now we could also do something called descriptive statistics in the data analysis. So we would go to data analysis, and we'll find the descriptive statistics feature, and we're going to put the input range. So that's going to be the full set of data. Let's see. Actually, you know what? Let's put this all the way to B1. That way we can include the title here. And then we'll say labels in the first row. Let's put the output range. Let's put that starting there. Let's do all the summary statistics and the confidence level. And then we'll say, okay. Now it's going to tell me I'm going to write over something, so that's okay. And now we get the mean, the standard error, the median, mode. But really all we're doing is we're looking and seeing, okay, well, we can get the mean using descriptive statistics, we can get the median, and we can get the mode, okay? Now, one thing to note with mode in Excel, it doesn't always give you all of the modes if it's multimodal. Even though it says you're going to do multi-modes, it doesn't always do it. So what I always do is if it's a small set of data, I copy it, paste it somewhere else, sort it from smallest to largest. So use the sort feature, smallest to largest, after you highlight it, and then go down and look through it. So 21, then we have two 23s, which is good because that matches here. And we go down a little bit further, all of a sudden we have two 30s, and we have two 33s, and we go to the rest of the data, there's nothing. So this is actually trimodal. We've got 23, we've got 30, and we've got 33. So really, there are three modes here, not just the single modes. So sometimes you actually have to go through and find all the modes by hand, which isn't too bad when there's a small amount of data, but if there's a huge amount of data, you would hope that it'd be actually found here, but it's not always. Now the trim mean and weighted average. Let's start with the trim mean. So again, we're going to use the personal vehicles, and we're going to use it in the sorted mode because we have to have first sort it from smallest to largest. Then we're going to delete the bottom 5% and the top 5% of data. Well, how do we do that? Well, first of all, what is 5% of 50? Because we have 50 data points. 5% of 50 is 2.5. That means we're going to round up to 3. So we're going to delete the top 3 and bottom 3 items. So we're going to delete those 3. And we're going to delete those three. Can't talk here. And that gives me this set of data. So basically, I've just kind of copied the data over here and then deleted the top three and the bottom three. And then I'm going to find the mean of the rest of the data. Okay. Well, we already know the mean was 173.24 from the previous page. And now the mean of the trim data is 138.318. So we can see that when we trim 5% off, it really does change the mean values. All right, now let's go back to our PowerPoint slide. Let's look at percentiles now. Well, if we're looking for the pth percentile, that splits the data into two parts where the p% of the observations have values that are less than the pth percentile. So it's going to be a specific spot in the data. And then 100 minus p% of the observations will have values greater than the pth percentile. Now we also can find quartiles. These are the 25th, 50th, and 75th percentiles, and they're also known as Q1, Q2, which is also the median, and Q3. So quartile 1, quartile 2, quartile 3. Now, Excel 2010 or newer works fine as a function to find percentiles and quartiles. Older versions, you have to actually do it by hand. You can't use the Excel because it'll give you the wrong values. Okay, so let's go look and see how we can do percentiles. All right, so I'll show you kind of a quick and dirty way to do the Excel version as well as the longhand version. So with Excel, we're going to use percentile.exe, and that's because that's the part we're going to use. There are other ones, but if we look here, percentile, there's a INC, but that's not the one we want to use with the kind of percentile we're looking for here. So we're going to use the EXC, and we have to sort the data from smallest to largest, and that's mainly for when we do it all by longhand. Otherwise, it really kind of does it for you. You don't have to worry about it when you do it with Excel. So we do the percentile.exe, highlight the data. It's going to be in this format. I put the $ in because I'm just going to copy everything over to the next ones, and all you have to do then is change what percentile. So for the 20th percentile, you put the 0.2. For the 25th percentile, you put 0.25, and then 0.65 and 0.75, and that is the position that's the 20th percentile, and the 25th, and the 65th, and the 75th. Now, for doing it longhand, we're going to come up with the same values here, as you can see, but we need to find different things. So the percentile is the one we're looking at here, so we're going to convert those to decimals. The number of data points, that's going to be n. Then we take n plus 1 times p, which is the percentile, and then we find the whole number of that value, and that's going to be our I. K is going to be the n plus 1 times p. The d is going to be the decimal value of the k. Then we're going to find m, which is the data point I plus 1 minus data point I. So I is going to be, again, whatever value we're looking at here, and then minus the data point, just the I. Then we'll take m times d, and that'll be the next row, and then m times d plus the data point I is going to give us the 20th percentile, or this 25th, or the 65th, or the 75th. So that's going to be the actual percentile. And I think I must have typed something wrong here because I wrote over copying something here. So this is actually the percentile. All right, so number of data points. Well, that's 8. There's 8 data points here. K, that's going to be n, which is 8 plus 1, so that's 9, times p. In this case, p is 0.2, so 9 times 0.2 is 1.8. And we can do it by using the equation up here. So we're going to take B13, which is the 8, plus 1 times 0.2, and that gives us our K. Now, I is just the whole number from K, so that's the 1. That's what's in the whole number position. And the decimal part is 0.8, and so that's going to be the D. M, that's going to be data point I plus 1. Well, I is 1, so data point 2, well, that's going to be 15, minus data point I, which is 1, which is a 13. So 15 minus 13 gives us a 2, and so that's just the A2 minus the A1. Now we're going to take m times d for the next part, and so we take the 2 times 2 times 0.8 gives us 1.6. And now we take that value and add the data point I, which is the first one, so 13 plus 1.6 gives us 14.6. And so again, we're just using the cells and referencing them and getting our equation or our calculation done that way. And that is the 20th percentile. And you can do the whole longhand thing with the 25th, the 65th, and the 75th, and you always get the same thing as you get if you do it with the excel.exe. All right, so let's go back to our PowerPoint. Now let's do box plots. Now, in order to construct a box plot, we need the following steps done. First, we need to find the 5-number summary. Well, what is the 5-number summary? Well, that's the minimum value, first quartile, second quartile, third quartile, and the maximum value. And we put them in ascending order on the horizontal axis or the vertical axis if you prefer to make them up and down. And then you're going to go from the bottom to the top. Then you draw a box encompassing the first and third quartiles, so it'll be kind of a box going around this. Draw a dashed vertical line in the box at the median, so wherever Q2 is, you're going to put a dashed line there. And then determine if a given observation is an outlier. First, we have to calculate the difference between the third quartile and the first quartile, and this difference is called the interquartile range, or the IQR. So therefore, the length of the box is equal to the IQR, and the span of the box containing the middle half of the data. Draw a line, or whisker, because it's a box and whisker plot or a box plot, that extends from the first quartile to the minimum data value, as long as that data value is not further than 1.5 times the IQR value from Q1. Okay, so we're going to go down this way, and as long as the 1.5 times IQR is further than the minimum value, we just draw a whisker to that minimum value. And then we also do the same thing. We draw a line to the maximum value as long as that maximum value is within 1.5 times IQR of Q3. Okay, and then if anything is beyond 1.5 times IQR, we'll make an asterisk, and those are considered outliers. Okay, so all of that in a picture format looks like this. So we have the min, Q1, Q2, Q3, max, which is way out here. And so we draw the box around Q1 to Q3. We draw the dotted line through the median. Then we found the 1.5 times IQR. That goes all the way out to here. And so our whisker goes to the min or to the 1.5 IQR, depending on which is the difference. And the smaller one is min, so that's where we're going to draw the whisker in this case. Now, in this case, the whisker only goes to the 1.5 times IQR because we have something beyond that, and that's going to be our outlier, which is starred. Okay. Now let's go look at calculations again. So box plots, what do we need? Well, first we have our data. And we need to find the min, Q1, Q2, Q3, max. Then we need to do the IQR calculation, 1.5 times IQR calculation. Then Q1 minus the IQR, which gives us the thing going to the left, and the Q3 plus 1.5 IQR, which gives us going to the right. And so for finding the min, we're just going to use the min function. For finding Q1, we're going to use quartile.exe. And again, this has to be done in 2010 or newer. This is 2016, so it works fine. And so we select our data, and then we want the first quartile because we're doing Q1, so we have the 1 here for the first quartile. Now, if we go to the next one, we're going to the second quartile, Q2, so that was going to be 2. And then the next one's Q3, so we're going to use the 3 for the third quartile. Then max, that's going to be how we find our max. IQR again is the Q3, which is the D5, minus Q1, which is D3. That gives us 12.5. And we take 1.5 times IQR, so that's going to be 1.5 times the D7, so it's going to give us 18.75. And then we can take Q1 minus the D8 and get this value, and then we can take the Q3 minus or plus the D8 and get that value. Okay, and so then we can hand draw this if we have to, or we can actually use Excel. If on the newer versions, you can actually do box plots. So you insert and you choose a graph, and you go down here to the box and whisker, and that's what it looks like. I'm not going to insert it because we've already got it, but that's how you would choose to get the box plot. Now, notice this one doesn't have any outliers. The IQR goes from negative 10.5, well, the minimum is less than that, so we're okay there. And it goes all the way up to 39.5. Well, the max is less than that, so it goes just to the whisker goes to the max value, and we're okay there. Now that gives us the mean of 15.625 for that whole set of data. Well, what if we change and we get a higher mean? Let's change that last point to 45. We can see now that the mean goes up. Now everything else is going to stay the same. So all these values do not change. All that changes is that max. Okay, the rest of the values besides the max do not change. And so then when we plot it, this becomes an outlier. That 45 is an outlier. And we only draw our whisker to the value that's the one below that, which is to 22. So we draw our whisker out to 22. Here we draw it down to 3 still. And we still have our box around Q1 and to Q3, and then median, we have our dashed line here. And then we have our star or asterisk out there at that 45, which is the outlier. All right, now let's go back here. Now let's look at measures of variability. We have range. That's the simplest measure where you take the max minus the min. We also have a variance, where the average of the squared differences between the observations and the mean. For the sample, that's S squared, and for the population, that's sigma squared. Now, for the standard deviation, what we do is we take the square root of the variance. So the sample becomes S, the population standard deviation becomes sigma. We can also find the coefficient of variation. It's a relative measure of dispersion and adjusts for differences in the magnitude of the means. And we use it to compare data sets that are of different mean ranges. So maybe you have a mean of one of 15 and you have a mean of the other one of 5,000. If you're looking at the standard deviations of those two, they're not going to be the same level because you have such big differences in means. And so what you need to do is you need to take that standard deviation, divide it by the mean, times 100, and you get your coefficient of variation. Now we also have distribution shape. So that's kind of the skewness. And now this is a numerical measure of shape. Now if your data is skewed to the left, you're going to have the skewness that is negative. And here that means the mean is less than the median. Now, if your data is skewed to the right, the skewness is positive. That's the skewness is an actual number. And here the mean is going to be greater than the median. Now, if you have truly symmetric data, the skewness is going to be 0. And here the mean is equal to the median. So now let's go look at some calculations here for all the variability and the skewness. All right, so what we have is we have years, and then we have some metal values and income values. And what we're going to do is we're going to kind of look at the items we talked about: the variance, standard deviation, the range, and the coefficient of variation. And if we want to, also the skewness in the second part here. So variance, we're just going to use var, okay? But because this is just a sample, we're going to use var.s because that's a sample. There's also var.p and just plain old var. But since we're using sample data, we're going to use the var.s, and then we're going to highlight the data, and that gives us the variance for the metals. And similarly, we can use the var.s for the income, and we just use the data in the C column to get that variance. Now with standard deviation, we can just take the square root of the variance and we can get the standard deviations, or we can use the function standard deviation.s and use the original set of data, and that will give us the standard deviation of the metals or the income. Okay. Now we need to find the range. Well, that's just the min, or the max minus the min. So I did it longhand. I took max of the data set minus the min of the data set, and that gave me the range. Here I did the same thing, but changed the data set. All right, so here I wanted to find the coefficient of variation. Well, that's just going to be equal to the standard deviation divided by the range, not the range. What am I typing here? I don't have the mean. That's what I'm looking for. All right, so I get the mean over here so that we can do that. Never mind. I forgot to add in everything I needed. All right, so oops. So we're going to take the standard deviation divided by the mean and times 100. and we get our coefficient of variation. Now here, we're going to take and do, again, standard deviation divided by, now we're going to use the mean over here, and then again, times 100, and that's going to be our coefficient of variation for the income. Now this is really, looking at this is going to be the true way to kind of compare things of way different mean values. Now these mean values, while they look 3 times different, these are still pretty close. So as you can see, the standard deviation, it was larger for the metals, and the coefficient of variation is larger here for the metals as well, and then this is smaller over here. But when you get to the things, say like 5,000 or 6,000, maybe here, keep it down here at 8, then your variances are going to be hugely different, as are your standard deviations after you take the square root to get the deviations. And so, but you're not going to be able to tell anything because your numbers here, if it's 5,000, that's already going to give you huge standard deviations most likely. And when you have small numbers over here, that's usually going to give you small standard deviations because there's not a lot of variance between 1 and 8, or so that's why I use that coefficient of variation. Now remember, we also are going to look at skewness. Now this metals is skewed left negative, okay? And if we look, we have our mean and we have our median, and because the mean is smaller than the median, it's negatively skewed. Now here we have the mean is greater than median, and so we have it's positively skewed here. So that's going to be kind of, we can look at it as mean and medians and say, okay, well, we know it's going to be a positive skewness. Here it's less than, so it's going to be a negative skewness. Or we can actually calculate the skewness. And there's also a formula for that in Excel, and that's just equal, and then SK should get us there. And we're going to just use that one. We're not going to use the population one. Hit enter, and we get the same value here. If we copy that, that gives us the same value there. So we can do it by hand, or we can do this. And this again was just found using the data analysis, and then the descriptive statistics, and then that gave us all the descriptive statistics for the metals and for the income. All right, let's move on. Z-scores. Well, Z-scores are computed as shown below here. We take the x minus x bar over s. With x being the sample value, the x bar and s are the sample mean and the sample standard deviations. And so as long as we know those items, we can calculate the Z-scores. Now the Z-score is a unitless measure stating the distance a given sample is from the mean and standard deviations, and it can be positive or negative. So if you have a Z of, say, 1.5, that means your data value is 1.5 standard deviations above the mean because it's positive. If you had a standard deviation or a Z-score of a negative 0.2, that's going to be 0.2 standard deviations below the mean because it's negative, so it's going to be below. Now, when we found outliers in the box plots, that was the asterisk value. Now we can also find outliers using Z-scores, and that's going to be any Z-score that's greater than 3 or less than 3 is going to be an outlier. So let's look and see how we can calculate outliers. So here we have Z-scores. And so what we have is part of a set of data. There's a lot of the data. And so we have motion pictures and number of weeks it was in release. So that's what this column is. And so what we can do is we can do descriptive statistics, and that will give us this whole set of data here. And again, that's data analysis, descriptive statistics. And what we can then do is we can find the Z-score for each and every movie here, all 100 of them. And it's really simple. All we're going to do is we're going to take E2 in this case, which is the data value, minus the G3. Well, G3 is the mean, okay? So that's what is important. And we're going to divide that by the standard deviation, which is right here, G7, okay? So E2 minus G3 divided by G7. Remember to put parentheses around your numerator, otherwise you're going to take E2 and then subtract off the division of G3 and G7, so you always have to remember to do that. And so that's how you get that value. And then once you get that one, you can just highlight the whole rest of the row or column rather, and Control D, and that will put them in all the rest of the way down. Now, you can go and you can search for outliers. Now, the way to find outliers is you can say equals if the absolute value of this number here in the previous column, so in this case H2, is greater than 3, then we're going to put H2 and then comma and then blank. Okay. And so that's how we're going to do that. And what it's going to do basically is it's only going to put what the value is if it's greater than 3. And so in this case, it found it was 3.05. So that's greater than 3. And what it's doing is it's looking for the absolute value of it. So it goes to this number and says absolute value of that is 3.05. That's greater than 3, so we're good. Now, if it had been negative 3.05, absolute value that is still positive and would make it actual outlier. And so then it would actually bring it over here as a negative 3.05. So it's just simplifying our equation by taking the absolute value of it and just doing it that way instead of saying, okay, if it's going to be less than negative 3 or greater than positive 3, do this. So it's shortening our equation we have to find. And so that's going to be one outlier. And then we go down here, that's our other outlier. And all the rest of them are blank because those are not outliers. And so basically it's putting in that blank value here. The H14 is the value that's put in here because it was greater than. So we got two outliers, the one here at 30 and the one here at 43. And if we did a box plot, we actually get the same two. We get 30 and 43. So box plot would get you the same thing as the z-score. Sometimes I think the z-score is easier just because that way you can kind of see more information about the standard deviations above and below the mean here. All right, so let's move on to the last part here. And this is relative location analysis. So Chebyshev's theorem basically states the proportion of observations that lie within k standard deviations from a mean is at least 1 minus 1 over k squared, where k is any number greater than 1. Now remember, over here, z-scores were going to be the basically how far away something is from the mean and standard deviations. And this is kind of doing the same thing, except now we're using k standard deviations above or below the mean, okay? And when you take it above or below, when you square it, it becomes positive, so it really doesn't matter. So let's say we have 2, okay? So that gives us 1 minus 1 over 2 squared, which is 4. So that's 0.75. So that means that 75% of the observations lie within 2 standard deviations of the mean, okay? And we could also do 4, and that's going to give us a 16 because 4 squared is 16. So that's going to be 93.75% of the observations lie within 4 standard deviations. You could do any number here, but 2, 3, and 4 are going to be the key ones. 3, I think, is 88.9%. And so you can see as you go up, it's getting higher values for the number of observations that lie within that many standard deviations. Now the key here is this applies to all sets of data, no matter the shape of the distribution. Now, if we have a bell-shaped, we can use the empirical rule. So when the data is drawn from a bell-shaped distribution, one can get a better estimate of the percentage of observations that fall within a certain number of standard deviations from the mean. And so for bell-shaped and symmetrical distributions, 68% of the observations fall within 1 standard deviation of the mean, 95% fall within 2 standard deviations, and 99.7% or practically all the observations will fall within 3 standard deviations of the mean. And here you kind of see what it's looking like. So the normal curve looks like that. This is our mean value right here, and we're looking at 1 standard deviation above, so plus 1 standard deviation. Here we're taking 1 standard deviation below, so that's minus 1 standard deviation. Here's plus 2 standard deviations, minus 2 standard deviations, then plus 3 standard deviations, and minus 3 standard deviations. So that's kind of explaining how it is. So 34% is going to be how much of the how much of the population falls within 1 standard deviation of the mean above the mean. And another 34% fall below, so the total is 68% within 1 standard deviation. and that's 95% within 2 standard deviations. Or you could just, if you want to do only above 2 standard deviations, you just take the 34 plus the 13.5, and you get 47.5% of the data fall within 2 standard deviations above the mean. And then again, like I said, 99.7 within 3 standard deviations. All right, we can also look at measures of association between 2 variables. So that's covariance. This provides a direction of the linear relationship between 2 or more sets of random variables. Now the key here is with covariance, you cannot comment on the strength of the relationship. So a positive value of covariance indicates a positive linear relationship between the 2 variables. And on average, if x is above the mean, then y tends to be above the mean and vice versa. Now, a negative value of covariance indicates a negative linear relationship between the 2 variables. And again, on average, if x is above, then y tends to be below the mean and vice versa. Now, if you have covariance is 0, x and y have no linear relationship. Now, this is another calculation where Excel 2010 or newer is required to get the correct covariance. Otherwise, you have to calculate it by hand. Now, the correlation coefficient, or Pearson's correlation coefficient sometimes, R, describes both the direction, which is the covariance, and the strength of the relationship between the 2 variables in question. Now, the next page is going to give us examples of both positive and negative correlations and their strengths. So the top ones are positive. So if it's a perfect positive, R is going to be 1. Now, if it's a strong positive, you might be somewhere around 0.81. So it's not a perfect relationship, but it's still positive. It's still, if you drew a correlation trend line here, it would all be pretty close to that trend line, and you can tell it's always moving up. Now, if it's kind of weak, if you drew that trend line here, the data points are kind of further away from that trend line, and so you're going to get R, it's smaller, so 0.45. So 1 is perfect, and then as you go down closer to 0, that gets weaker and weaker and weaker as you go to 0. Now, another way, if they're negative, say if we have a -1, that's a perfect negative correlation. Now, if we can draw a trend line here, that's pretty good, that's pretty strong, so say that's -0.92. Now, like I said, if you're closer to that 0, there's no correlation. It looks more like a shotgun pattern on a piece of paper. There's just, you couldn't draw a line to make it look the best way any direction. You could maybe find something that way, but you could also find something that way. And it's 0.04, so that means it is positive, but really at that level, there's no correlation. So let's look at our last thing here. And that's the correlation and covariance calculations. So we have 2 sets of data. So going back to the movie data, we have opening gross sales, total gross sales. And so what we want to do is we want to compare the 2 columns of data. So with covariance, we're just going to use covariance.s. So we're going to find the covariance for the sample of data, okay? Because there's more than 100 movies produced that year. This is just the top 100 of them. And so we're going to use the sample covariance, and so that gives us 1603.056673. And with that number, all we can say is that it's a positive linear relationship. We can't say the strength, we can't say anything else. All we can say is it's positive. Okay. Now, if we want to find the correlation, which will tell us if it's positive or negative, as well as the strength, then we're going to use correlation. And that's just correl, and that's all you need to do. And then you just need to have the 2 sets of data. So highlight the first one, comma, highlight the second one. And so what we can say with this one at 0.887, it's a positive relationship, so we know that one already, but it's also a strong positive linear relationship because that number is close to 1. And so it's very strong. And so these 2 data sets are highly correlated between them. Now, one doesn't cause the other one. We can't say causation. All we can say is there's correlation. Okay. So hopefully all of this will help you this week with calculations in Excel, as well as doing calculations for different things that we're covering in this chapter.